Alright, today we're going to have a look at the solutions to homework of topic 8, quadrilaterals part B. Alright, first question. In rectangle, opposite sides also have equal lengths, right? So we should put yes here. And for square, opposite side also have equal lengths, so you should put yes here, right? And all sides have equal lengths. For parallelogram, sometimes this is true and sometimes it's not true, so sometimes here. For rhombus, all sides have equal lengths. Yes, of course. This is according to the definition of rhombus, right? For rectangle, all sides have equal lengths, not necessarily true. So sometimes true, sometimes not. And for square, all sides have equal lengths. That's true. Okay, for parallelogram, opposite sides are parallel. Yes, of course. This is a property of a parallelogram. Rhombus, opposite side parallel. Yes, because this is also property of a rhombus, right? Rectangle, opposite side are parallel. Yes, and for square, this is also true. Okay, for parallelogram, opposite angles are equal. Yes, this is a property of a parallelogram. For rhombus, this is also true. For rectangle, this is also true because all of the interior angles of a rectangle are 90 degrees. Of course, this is also true for squares, right? And for parallelogram, all angles are equal, not necessarily true. So sometimes true, sometimes not. Rhombus, of course, sometimes true, sometimes not. Rectangle, yes, because each of the interior angles is 90 degrees. Square, yes. Again, 90 degrees interior angles. Parallelogram have this property that diagonals bisect each other. Yes. And for rhombus, this is also true. For rectangle, this is also true. Squares, this is also true, right? Diagonals have equal lengths. For parallelograms, this is not necessarily true. Sometimes true, sometimes not. For rhombus, again, sometimes true, sometimes not. Rectangle, this is true, and for squares, this is also true, right? Any questions? All right, then let's have a look at the next one. Okay, number 2, a semicircle with center O has radius of 9 centimeters. What is the number of centimeters in the length of RQ? Diagonal of the rectangle shown here. Okay, the other diagonal of the rectangle is the radius of the circle, right? If you connect this point to the point O here, then you can see the other diagonal of the rectangle is the radius of that circle, which is 9 centimeters, right? And we also know the two diagonals in a rectangle are equal, right? So suppose we call this point P, then we know that RQ should equal OP, which is 9 centimeters, right? All right, next one. Question number 3. EFGH is a rectangle with area 48. If EGJI is a rectangle such that point H is on segment JI, what is the area of EGJI? Okay, let's draw a rectangle first. Okay, draw the diagram on the right. First of all, we have a rectangle EFGH, and then we have another rectangle such that H is on JI, so the other rectangle must be somewhere here. So this point is J, and this point is I, right? And we know that triangle HEG, which is this rectangle here, and triangle, a rectangle IEGJ. They share the same altitude from H to EG, right? You see that? So we know that the area of IEGJ should equal twice of the area of the triangle HEG, right? Can you follow me? On the other hand, triangle HEG is half of rectangle EFGH. Therefore, we know the area of EFGH is twice of the area of the triangle HEG, right? And therefore we have IEGJ equals the area of EFGH, which is 48. Any questions? Okay, and let's have a look at the next one then. I'm in the midpoint of segment AB on square ABCD. Okay, let's draw a square ABCD first. Suppose ABCD is a square like this. Then M is the midpoint of AB, so M is here, right? And if AC and BD meet at O, okay, AC is here, another diagonal is BD. They meet at a point O here, and MO is 4. So let's connect M and O. And this segment is 4, and it asks you to find the area of the square ABCD. Okay, so we can use some fractions here. So because we know BM over BA equals BO over BD, which is 1 over 2, right? Because M is the midpoint. And we also know that angle MBO, which is this angle here, equals angle ABD. Because they're the same angle. And therefore we know triangle BMO is similar to triangle BAD by SAS similarity, right? And therefore we know AD must equal 2 times the length of MO, which is 8, right? And therefore we know the area of the rectangle or square ABCD should be 8 squared, which is 64, right? Okay, have a look at the solution here. Any questions, just let me know, okay? Alright, if no questions, let's have a look at the next one. Number 5, diagonals of a square TYUI meet at a point M. Point K is on side TY, and it also tells you that TK equals TM. And it asks you to find angle MTK and angle TMK. Of course, if you know the angle MTK, you can find TMK immediately, right? Okay, first of all, we know that angle MTK equals angle UTY, which is 45 degrees, right? And because TK equals TM, we have angle MKT equals angle TMK, right? And in triangle MTK, we have angle MKT plus angle TMK equals 180 degrees minus angle MTK, right? Which is 135 degrees. Therefore, we know angle TMK is 135 degrees over 2, which is 67.5 degrees, right? So the key is to find angle MTK here, which is 45 degrees in a square like this, right? Can you follow me? Pretty straightforward question, right? Okay, have a look at the solution here and let me know if you have any questions. Alright, if no questions, let's have a look at the next one. Okay, prove or disprove the following statements. Let M be the midpoint of AB, triangle ABC is isosceles with AC equals BC if and only if CM bisects angle ACB. Okay, we have a statement if and only if, so if you want to prove this is true, you should prove either direction of the statement is true, right? So first of all, we can assume triangle ABC is isosceles. Okay, first of all, assume triangle ABC is isosceles with AC equals BC. Then you need to prove that CM bisects angle ACP, right? So if AC equals BC, This is A, this is C, this is B. AC equals BC. Okay, if we assume triangle ABC is isosceles with AC equals BC, then we know that angle CAM must equal angle CBM. And also AM equals BM. This is a property of an isosceles triangle, right? Therefore, we know triangle CAM is congruent to triangle CBM by SAS, right? Therefore, corresponding angles are equal. In particular, we know that angle ACM should equal angle BCM, right? Therefore, CM bisects ACB. So you have proved that from the left side to right side is true. Next, we need to prove the other direction. We need to assume CM bisects angle ACB, right? If CM bisects angle ACB, you need to prove AC equals BC. If you can prove that, you can prove the if and only if statement, right? So suppose we have a triangle here. M is midpoint. If you assume CM bisects angle ACB by angle bisector theorem, can you recall this theorem? By angle bisector theorem, we have CA over AM equals CB over BM, right? And because we have M in the midpoint, which is AM equals BM, then we have CA equals CB, right? Therefore, we can prove triangle ACB is actually isosceles triangle with CA equals CB, right? Therefore, we can make the final statement. Triangle ABC is isosceles triangle with AC equals BC if and only if CM bisects angle ACB, right? Remember, if you want to prove a if and only if statement is true, you need to prove both directions. Okay, have a look at the solution here and let me know if you finish, okay? Alright, then let's have a look at the next one. Question number 7. Okay, this time we have a trapezoid ABCD with the length shown here. And we need to find the area. Okay, in order to find the area of a trapezoid, we need to know the two bases and altitude, right? So here we know the length of BC, the altitude here, and as long as you can find the other base, you can find the area of the trapezoid, right? So in order to find the other base, we can draw CF perpendicular to AD, and let's call this point E. Then let E and F be the theta perpendiculars from B and C to AD respectively. Okay. First, you need to state the auxiliary line you are drawing here. So you should state let E and F be the theta perpendiculars from B and C to section AD respectively. Then we have BE equals CF, right? Because BCFE is actually a rectangle, right? Which is 24. And EF equals BC equals 12, since BCFE is a rectangle. And by using the Pythagorean theorem, we know that AE equals square root of AB squared minus BE squared, right? Then we can find the length of AE, which is 30 squared minus 24 squared, and that's square root of 324, which is actually 18, right? And we also know that FD can be found by using Pythagorean theorem as well, which is CD squared minus CF squared. And this gives us 25 squared minus 24 squared, which is square root of 49, which is 7, right? Therefore, we know this length is 18, and FD is 7, and EF is 12, right? Therefore, we know the length of the other base equals AE plus EF plus FD, and that's 18 plus 12 plus 7, which is 37, right? Therefore, we know the area of the trapezoid ABCD can be calculated by 1/2 of the first base plus the second base times the altitude or height, which is 588. Okay, did you get this correctly? Okay, have a look at the solution here and let me know if you have any questions, okay? Alright, if no questions, let's have a look at question 8. Okay, first of all, let's draw a diagram to illustrate this situation here. So basically you have a quadrilateral ABCD, which is a trapezoid. Okay, let's draw the trapezoid first. And we know that AB is longer than CD, right? So AB is here, CD is here. AB is 20 and CD is 12. And then it says we need to find the ratio of area of triangle ACB to the area of ABCD. Okay, first of all, we could draw a perpendicular segment here. And let this point be E. So let E be the foot of perpendicular from C to section AB, right? Then we can let EC be H. Then we know that the area of triangle ACB can be calculated by using 1/2 of the base AB times H, right? Which is 1/2 of, we know AB is 20, right? We know the length of AB is 20 and times H, so this gives us 10H, right? And on the other hand, we know the area of ABCD trapezoid is 1/2 of the first base plus the second base times the altitude H, which is 1/2 of AB is 20 and CD is 12 times H, and this gives us 16H, right? Therefore, we know the ratio of the area of the triangle ACB to the area of the trapezoid ABCD is 10H over 16H, which is 5/8, right? Okay, of course, the method to solve it is more than one. You could use some other method, okay? And have a look at the solution here, and you can compare yours with mine here, and let me know if you have any questions, okay? Okay, if no questions, let's have a look at the next one. Each side of a equilateral triangle is 8 inches long, and altitude of this triangle is used as the side of a square. So this is the side of the square, right? So if you want to find the area of the square, you need to find the length of this side, right? And if you let ABC be the triangle and AD be the altitude, then the triangle ABD is actually a 30, 60, 90 right triangle, right? And then we can immediately write AD is actually square root 3 over 2 times AB, right? You recall this? And this gives you 4 square root 3. Therefore, we know the area of that square is area of the square area of the desired square is 4 square root 3 squared, right? And this gives us 48. Okay, any questions? Okay, then let's see the next one. Trapezoid ABCD is divided into 4 congruent trapezoid as shown here. Given AB is 4, CD is 8, find the sum of the lengths of all line segments in the figure. Okay, we could let A be the length of the longer base of the smaller trapezoids and B the length of the shorter base. Since EF is a leg of EFGH, so let's call this point G, this point is F, and this point is E, and this point is H. EF is a leg of EFGH and is also a shorter base of EFBC, right? The legs of these small trapezoids have length B as well. From the given information, we have A equals AB, which is 4, right? And also we have A plus 2B equals CD. Because if this length is A, this length is B, right? And this length is A, this length is A, and this length is B, this is B. Although this is A, this is A, and this is B, this is A, this is A, right? And therefore we know B is actually 2, right? And the diagram has 4 segments of length A. You see that? Yes?
I think you mislabeled A and B on the tab.
Yeah, sorry about that. Yeah, I also found that A is a longer one, right? A is not the shorter one. So A is here. B is here. Okay, so we have 1, 2, 3, 4 A's and 7 B's, right? And therefore the parameter, sorry, not the parameter, the sum of all the lengths here shown in the figure is just a 4A plus 7B, right? Which is 30. Okay, any questions? Okay, then let's see the next one, question 11. What is the ratio of the area of shaded square to the area of the large square in the figure at right? Okay, so note that if you call this point E, this point F, and this point G, and this point A, and if you connect EG, then we know that the area of the shaded triangle EFG actually equals that of triangle AFG, right? You see that? Therefore, the shaded square has area equal to triangle AEG, right? This triangle here. Large square is made up of 8 triangles like this, right? Which is congruent to triangle AEG. Therefore, we know the shaded area is just 1/8 of the entire square, right? Any questions? No? Okay, then let's see the next one. A street has parallel curves 40 feet apart. A crosswalk bounded by 2 parallel strips crosses the street at an angle. The length of the curve between the strip is 15 feet and each strip is 50 feet long. Find the distance between the strips. Okay, we know the crosswalk is a parallelogram with base 15 and height 40, right? And therefore its area is given by 15 times 40, which is 600. Then suppose we let the distance between the stripes be h. Then the crosswalk is also a parallelogram with base 50 and height h, right? And therefore we know 50 times h should also equal 600, right? And this gives us h equals 12, which is the desired length in this question. And because it's a simple question, you don't have to draw the diagram, right? Any questions? Okay, if not, let's have, yes?
I don't really understand the question, so can you draw the diagram? Like, I'm not sure which curves we.
Okay, okay, let me have a look at that. Yeah, the diagram is pretty simple. So basically it tells you need to draw 2 lines. This is a street, right? And crosswalk bounded by 2 parallel strips crosses street at an angle. So we have another crosswalk here. it tells you that these two curves are 40 feet apart, right? And you also know the length of the curve between the strip is 15. And each strip is 50 feet long. Then that means we know that this length is 50, right? So if we consider the parallelogram here, then we can use this area to solve this question. First of all, its area can be calculated by 15 times 40, right? On the other hand, we also know that equals 50 times the distance between the strips, which is h, right? Therefore, you can calculate h is actually 12, right? Any questions? Oh, okay. Then let's see the next one. Okay, this time we are given a diagram like this. Sorry. Okay, in a rectangle ABCD, we have AB equals 8, BC equals 9, H is on BC, with BH is 6, E is on AD with DE equals 4. Line EC intersects line AH at G, and F is on line AD with GF perpendicular to AF. And ask you to find the length of GF, right? Okay, first of all, because we know BC equals 9, then we have CH equals BC minus BH, which is 3. So CH's length is 3 here. And since ABCD is a rectangle, then we have AD equals BC equals 9, right? And therefore we have AE equals AD subtracted by ED, which is 5. So AE here is 5. And because we also have segment CH is parallel with segment AE, or line AE, doesn't matter. We have we have angle GCH equals angle GEA. GCH is here. GEA is here. And also angle GHC equals angle GAE. This angle here and this angle here. And therefore we know triangle GCH must be similar to triangle GEA, right? GF is altitude of triangle GEA, GF is here. And the corresponding altitude of triangle GCH has length GF minus CD, right? You see that? That's the altitude of triangle GCH, right? And by similar triangles, we have GF minus CD over GF. That's a ratio between the two heights or two altitudes, right? That should be equal to the ratio between two corresponding sides, which is, we can use CH because CH is known to us now, over EA. And that is 3/5, right? Since ABCD is a rectangle, we have CD equals AB equals 8. Therefore, substitution and cross multiplying can give us 5 times GF minus CD equals 3GF, which means 2GF equals 5CD, right? Which means GF is 5/2 times CD, which is 5/2 times 8, and that gives us 20. So length of GF is 20, right? And the key is to use a pair of similar triangles here. Sorry, there is a typo here. This should be AD equals BC. Okay, thanks. Okay, any other questions? No? Alright, then let's see the next one. Okay, question 14. Rectangle ABCD. Okay, let's draw a rectangle first. We have AB equals, okay, let's say this is point A, B, C, D. AB equals 16, AD equals 5, F is on AB, and G is on CD, such that FG, BD, and AC are concurrent at point O. Okay, let's connect BD. Okay, AC and BD and AC crosses point O, right? And we have another section GF, which also crosses this point. So let's call this is G, this is F. F is on AB and G is on DC. We need to find the area of FOB plus GOC. Okay, since the diagonals of a rectangle bisect each other, we know that AO should equal OC, right? And vertical angles are equal, so AOF equals angle COG. Sorry, this angle equals this angle here. And since sides AB and CD are parallel, we have angle FAO, which is this angle here, equals this angle here, right? GCO. Then we can have a pair of congruent triangles. AOF is congruent to COG, right? So let's say because AO equals OC, angle AOF equals angle COG. and also AB is parallel to CD. This gives us angle FAO equals angle GCO. And then we have triangle AOF is congruent to triangle GCO by ASA congruence, right? Then we have the area of FOB plus GOC is actually FOB plus AOF, right? So the area of FOB plus AFO is just the area of triangle AOB, right? And we know that right triangle ADB has area 1/2 of AD times AB, which is 40, right? And we also know that AO is a median in triangle ABD, right? Because this side equals this side. Then we know AOB, the area of AOB should equal 1/2 of the area of triangle ABD, which is 20, right? Okay, if you don't have any questions, you can take a 8-minute break. Please return before 8:40, 40 past 8. Alright, question number 15. In a rectangle ABCD, okay, another rectangle. Okay, suppose this is a point A, B, C, D respectively, and we know M is midpoint of BC. So M is here. Point P and Q lies on A, B, and DC respectively, such that PB is 4/3 of BC. Okay, so we have a point somewhere here. And a point somewhere here. Angle PMQ is a right angle, and we need to find the ratio between PM and MQ. Okay, first of all, we know angle B equals angle C equals 90 degrees. And angle QMC is 180 degrees minus angle QMP, then minus angle BMP, right? And then that's actually 90 degrees minus angle BMP, which equals angle MPB, right? Therefore, we could make use of a pair of similar triangles. Note that triangle QMC must be similar to triangle MBP by AA similarity, right? Therefore, similar triangles gives us equal ratios because corresponding sides are proportional, right? So PM over MQ is PB over MC, right? Which is 4/3 of BC over MC is 1/2 of BC, right? Then we can cancel BC here, and that gives us 8/3, right? Okay, have a look at the question here. Any questions, just let me know, okay? All right, if no questions, let's see the next one. Question 16. Okay, we have a trapezoid ABCD here. So first draw a trapezoid. A, B, C, D. Angle A equals angle D, which is 45 degrees. And angle B equals angle C, which is 135 degrees. And we also know AB is 6, right? Okay, if we draw perpendicular lines like this, and let the theta perpendicular lines be E and F, then we know, if you know the length of VA, then you can find the length of AE and FD, right? Then if you let the desired length BC be X, this length is also X, right? And we also know the area of ABCD, which is 1/2 of the sum of the two bases times the height. The height is also known if you consider this 45, 45, 90 triangles, right? So basically we'll have an equation in terms of x, then we can solve length of x, right? So let's start from the very beginning. So if we let, okay, first of all, because we have some auxiliary lines, you should state how did you draw the auxiliary lines like this. So we could say let E and F be the feet of perpendicular from B and C to line AD, segment AD. Then triangle AEB and triangle CFB are both 45, 45, 90 right triangle, right? Therefore, we have AE equals BE equals CF equals DF, and each of them is just AB over square root 2, right? And that's actually 6 over square root 2, and this gives us 3 square root 2, right? 3 square root 2 here, 3 square root 2 here, and here, right? And then we can let BC equals X. Then we also know that EF is also X because BCFE is a rectangle, right? Then we know the area of the trapezoid ABCD is calculated by 1/2 of the sum of the first base plus the second base plus 3 square root 2 plus 3 square root 2, right? Times the height, which is another square root 2, 3 square root 2. And the area is given here, which is 30. Therefore, we have an equation in terms of x, which is 2x plus 6 square root 2 times 3 square root 2 equals 60, right? And then we have 6 x plus 3 square root 2 times 3 square root 2 equals 30. And then we know x equals 2 square root 2, right? So the final solution is BC equals 2 square root 2. Okay, have a look at the solution here and let me know if you have any questions, okay? Next question then, question 17. So here we have a circle. A circle is drawn through the vertices of a square ABCD, and point X is on minor arc AB. So this is a minor arc AB. Given that XAB, the area of XAB is 1, and the area of XCD is 993. Then can you find the area of XAD plus XBC? Okay, we can let S be the side length of ABCD. And ABCD is a square, right? Then the height from X to CD. Must be S greater than the height from X to AB. Right? The difference is S. Then we can let the height from X to AB be H. Then we have 1/2 of H times S equals 1, right? Because it says the area of triangle XAB is 1. So we have 1/2 of S times H equals 1. And also 1/2 of H plus S times S equals 993, right? from the given information here. And this gives us, first of all, HS equals 2, right? And also HS plus S squared equals 993 times 2, which is 1986, right? And then we can use equation number 2, subtract it by equation number 1. This gives us S squared equals 1984, right? Which gives us the area of the square, right? Which means area of ABCD is actually 1984. And we want to find the sum of the area of XAD and XBC. Okay, let's connect these 2 points. XAD is here, XBC is here. Now we can let the distance from X to AD be, for example, T. Since ABCD is a square, the distance between AD and BC is S, right? And the height from X to BC, or the distance from X to BC, is S minus T, right? Can you see that? So if you let this distance is T, then this distance is, of course, S minus T, right? Then we have the desired sum of areas, XAD plus XBC, can be calculated by 1/2 of T times AD plus 1/2 of S minus T times BC, right? And of course, AD equals BC equals S, so this gives us 1/2 of TS plus 1/2 of S minus T times another S, right? Which can be simplified to 1/2 TS plus 1/2 S squared minus 1/2 TS, right? And actually we can cancel the 2 terms here. So this gives us just 1/2 of S squared. And we already know the S squared here. Then that's 1/2 of 1984, right? And that area is 992. Okay, have a look at the solution here and let me know if you have any questions. Okay, question 19. P is inside a rectangle ABCD. PA equals 2, PB equals 3, and PC equals 10. Find PB. Okay, first of all, let's draw the corresponding rectangle. And you have a P somewhere here, right? So A is here, B is here, C is here, and D is here. Then we have PA, Okay, let's say P is here, and PA is given, which is 2. And PB is here, which is 3. PC is 10. And PD is the desired length, right? Well, it seems that we could make use of some auxiliary lines. So probably we can draw altitudes from P to the size of the rectangle. Okay, draw a perpendicular line here and draw another perpendicular line here. And let's call the feet X, Y, Z, and W here. Okay, so first of all, we should state that draw altitudes from P to the size of ABCD at points X, Y, Z, and W respectively. Then, since ABCD is a rectangle, we have AD is perpendicular to AB, right? Because PX and AD are both perpendicular to AB, so we have PX is also perpendicular to AB. Then we know that AD must be parallel to PX. We also know that PX is perpendicular to CD, right? Well, you should use a line here. And therefore, angle XPZ is a straight line, right? Yeah, because when we draw the auxiliary lines, we draw it like this. PX is perpendicular to AB, PY is perpendicular to BC, and PZ is perpendicular to CD, and PW is perpendicular to AD. We haven't proved that XPZ is actually collinear and PWY is actually collinear, right? So in this way, we have proved XPZ is a straight line. That means XPZ is collinear. And similarly, angle WPY is also straight, right? Which means XPY is collinear. And therefore, we know AXZD is a rectangle, and BXZC is also a rectangle, right? Two rectangles. And therefore, we know AX must equal DZ, right? And also BX equals VC. We can then use the Pythagorean theorem to find, first of all, AP squared equals AX squared plus PX squared, right? And CP squared, we have 1, 2, 3, 4, 4 hypotenuse, right? Therefore, we have 3 Pythagorean formulas. CP squared is CZ squared plus VP squared. And also BP squared equals BX squared plus PX squared. And DP squared last hypotenuse equals DZ squared plus PZ squared, right? So adding the first equations and the last two equations, we have AP squared plus CP squared equals AX squared plus PX squared plus CZ squared plus DP squared, right? Which equals DZ squared plus PX squared because AX equals DZ, right? Plus CZ is XB, so that's BX squared plus PZ squared. And this gives us, we can rearrange the terms here, so we can combine PX squared plus, combine BX squared plus PX squared because we have it here, right? And combine DZ squared plus PZ squared, right? Because we can find it from here. Therefore, the first sum gives us BP squared. The second sum gives us DP squared, right? And therefore, we have PD squared equals PA squared plus PC squared minus PB squared, which is, well, we know PA is 2, so that's 2 squared. We know PC is 10, and we also know PB is 3, right? And eventually we have PD squared is 95. Therefore, we know PD is square root of 95. Okay, have a look at the solution here. Any questions, just let me know, okay? Again, it's a combination of geometry and algebra. Okay, if you have no questions, let's have a look at. Okay, last time I also give you some extra questions, right? So because we are running out of time, so I'll just give you the solutions to the last one here, okay? Well, let's consider this question here. Isosceles trapezoid ABCD with AB is parallel to CD is inscribed in a circle with radius 10, such that center of the circle is inside ABCD. Isosceles trapezoid CDF with CD parallel to EF is inscribed in the same circle, but the center of the circle is not inside CDF. So the diagram is shown here to you. And given that AB equals EF equals 12, and CD equals 16, can you find the area of ABCD and CDF? Okay, first of all, probably we can connect the center of the circle, right? So first of all, let's connect the center of the circle O to the vertices of the trapezoid A, B, C, D. And since we somehow want to use the fact that the trapezoid is inscribed in a circle, so we have OA equals OB equals OC equals OD, which is the radius of the circle 10, right? We need a height, so we can draw the height through O, since this will build right triangles in which we already know the hypotenuse. So we could let x and y be the feet of the altitudes from point O to AB and CD respectively. So here, I'm not gonna write all of the statements here, okay? So just remember how we draw the auxiliary lines in the diagram. So x is here, y is here, xy is perpendicular to both AB and CD, right? And let's extend xy a little bit and let the foot here be point Z. Again, xy is parallel to CD, AB, and EF, right? And since AO equals BO and XO equals XO, of course this is obvious. We have triangle AXO is congruent to triangle BXO, right? Together with AXO equals angle BXO, of course, by SAS. Sorry, I think we should use the property HL, right? Hypotenuse leg, because both of the two triangles are right triangles. Or if you don't use HL, we know AO equals BO, XO equals XO, and of course AX should equal XB. Then according to SSS, so you could write either HL or SSS here, right? Whichever you like. And therefore X is midpoint of AB, so this length equals this length. Similarly, Y is also midpoint of dy of CD, so dy equals YC, right? And therefore, let's say AX equals BX, and similarly, it could also prove that dy equals CY. and therefore ax equals bx equals 6, because we know ab equals 12, right? And dy equals cy equals 8. Then we can now use Pythagorean theorem on triangle XOA and triangle DOY to determine that XO, this side, and length of YO, right? So XO is square root of AO squared minus AX squared, which is, well, AO is 10 and AX is 6, so we know that's 8, right? And similarly, OY or YO equals square root of DO squared minus dy squared, which is 10 squared minus 8 squared, which is 6, right? And therefore we know XO plus OY is 14, which is the height of the trapezoid, right? And therefore the area of ABCD can be calculated, which is 1/2 of AB plus CD plus times XY, which is 1/2 of 12 times 16 times 14, right? Sorry, there should be plus sign here. And that area is 196. And now we can find the area of the other trapezoid CDEF. We could break the problem into right triangles as before, or we could be a little more clever and apply what we have learned about triangle AOB to triangle EOF. Well, use similar method, we can show that AO equals BO. And AB equals AF. Sorry, AB equals EF. Let's use a different color here. And BO equals FO, right? Sorry, my bad. AO equals EO like this, AB equals EF like this, and BO is equal to FO. Then we have triangle. Again, I'm not gonna write all of the statements here, okay? So we can prove triangle AOB is congruent to triangle EOF by SSS, right? And therefore the altitude from O to AB should also equal to the altitude to EF, right? Therefore, we know XO should equal ZO, right? which is 8. And moreover, since CD is parallel to EF and OZ is perpendicular to EF, we have OZ is perpendicular to CD. And Y is the foot of the altitude from O, and OZ passes through Y, so the height of CDEF is YZ equals OZ minus OY, which is 2, right? And therefore we know the area of CDEF can be calculated by 1/2 of the sum of the two bases times the altitude YZ, and that is 28, right? Okay. Have a look at the solution here. Any questions? Okay, so that completes our today's lesson, and the homework of today's lesson is to try to correct any question you haven't done correctly, okay? And there are 2 questions we haven't covered in this lesson, and if you haven't completed them, try to complete by yourself. And if you still have any questions, we can talk about them at the beginning of our next lesson, okay?